Hello everyone, today we are going to present about our digital logic project. This is our group member. I'm Siu Ching and we have Ija, Abra and Hui Ting. This is the introduction. So in this assignment, students will have to collaborate in a groups of 4 to implement a digital logic circuit capable of transferring data from a specific computer in Lab A to a designated computer in Lab B. The objective is to gain practical experience in circuit design while identifying and troubleshooting errors throughout the process. This project also encourages self-exploration, allowing group members to conduct online research to develop an innovative solutions and creative design. In addition to deepening our understanding of logic and the utility of JITs, the project also helps to enhance our communication skills and collaboration spirit by requiring participants in group meetings, presentations, reportings, and demonstration sessions, which also involves showing and testing the result by publishing an offline video recording. As for our problem background, there will be 6 computers in Lab A which are connected to 6 computers in Lab B throughout a single cable. Students are tasked to transmitting a user-defined number of data packets from a source of computer in Lab A to a destination computer in Lab B. The challenge lies in ensuring successful data transmission throughout a single cable, with the process will stop when all packets have been transmitted correctly. Besides, synchronization is essential to maintain accurate communications between the computers too. Other than that, a clock signal will regulate the flow of data, while a clock-enabled pin will ensure the data transmission occurs only under the correct conditions.
So now I'm going to talk about the suggested solution for the problem met. First of all, this is the broad diagram for the system design. Firstly, for the data transmission, the data packets will move from a computer in Lab 1 to Lab 2 via a single cable. The user needs to turn on the power switches in both labs to get the computers running, and also select sending and receiving computers and input the number of packets to transmit. Next, for activation, ready TRX button, password, power supply, comparator, and pulse inputs are required to activate the clock enabler for controlling data move, making sure packets go out steadily. Furthermore, for the monitoring, the counter will track the number of packets transmitted, while the comparator will match the count with the user input and stop transmission automatically. The clock enabler will also stop when the desired number of packets have been sent. The screen will show the total packets sent for the user discharge. Last but not least, there are a few advanced features in the system design. Firstly, there is password. The password protection will enhance the security of the circuit. Furthermore, the fault detection will identify issues during transmission and require user intervention to resolve them. Once all packets are successfully sent, the fault detection monitor will automatically turn off. Last, the dashboard will provide a user-friendly interface displaying the status of computer power, security verification, and data transmission process.
So now I'll be talking about the requirements, as well as more about the feature scaling, the feed-forward networks, as well as the feature selection. For the feature scaling, it means essentially is that we're ensuring all the signal levels in the circuit are standardized and proper scaling of clock pulse to maintain a synchronous operation across all the flip-flops. Feed-forward networks. The counters in the combinational circuit is designed as a feed-forward network where the output of logic gates are fed to the D flip-flop without feedback loop to ensure stable operation. And for the feature selection, we have selected and implemented these components, which included a 4 D flip-flop counters, which are all counter-ups, logic gates, AND or XOR and NOT, clock enabler comparators, a multiplexer, demultiplexer, LED light, and decoder. So the system implementation, we have designed and implemented this circuit using DEET, refer to the block diagram of suggested solution and project requirement to ensure all the objectives were met. So here is our design for Lab 1 and Lab 2, and here we have shown that we have used for Lab 1 and multiplexer. as to encode all the data and data packets from the source and from the computers. The multiplexer selects one of 6 input sources based on the 3-bit user-defined select signals and transmits the data through its output, which is connected to an AND gate. A demultiplexer implemented to the decode and distributes the transmitted packet to the target computers in Lab 2. Demux then decodes the data based on the same 3-bit select signal and to deliver it to the appropriate computer in Lab 2, completing the transmission process. And here we can see that we have implemented an AND gate. This AND gate in particular has a second input which is coming from the clock signal generated by the 4D flip-flop counter to ensure that synchronization to all the data transmission. And now to verify power status of computers. Power signals from the 6 computers in Lab 1 are combined using an OR gate, and the same is done in the computer in Lab 2. The outputs of these OR gates are fed into an AND gate to ensure at least one computer in each lab is powered. If these conditions are met, the clock enabler is activated, allowing the counter to initiate packet transmission. 4D flip-flop counter and counter-ups. A 4-bit D flip-flop counter is implemented using XOR and AND gates. Counts transmitted packet and displays the count on a hexadecimal display. Comparators verify the counter output against the user-defined maximum packet limit, and the counter holds when the transmitted packet count matches the maximum limit, indicating transmission completion, which then prevents the transmission of excess packets. And finally, to clock enabler. This is a critical control of the mechanism that ensures the counter operates only when all the conditions are met, which is in total 5. The first condition is one computer in each lab is powered on. The pulse clock is available, which we have named in the Deeds Tricks clock. Transmission system is ready, which we have named Ready Tricks. Clock comparator, which verifies the transmission packet count is less than or equal to the user-defined maximum limit. Compares the counter transmission packet counts with the user-defined value, as well as password verification for security.
Next, I'm going to explain about the advanced features that we added in our system to increase reliability. So the first feature is password comparator. It can enhance system security as part of the clock enabler function, as we mentioned in the previous part, and we have used a 4-bit comparator to validate the user's input against a predefined password. As shown in the picture, we can set a 4-bit predefined system password, and the comparator will compare it with the user entered password, and if both inputs are matched, the output will be true, and the logical true will serve as an input to the clock enabler, ensuring password verification is successful. Other conditions such as power on, ready TRX, pulse clock, and packet count limit are met to activate the counter. The second feature is advanced monitor dashboard. This monitor dashboard provides a real-time system status updates using a 3 to 8 decoder and also LED. The input signals is from A0 power status from computers in Lab 1 and Lab 2, A1 clock comparator status, and A2 password verification, and the LED will light up based on the input signals received by the decoder. Y0 indicated power status, comparator, and password verification are all non-functional, while Y1 represents that computers in both labs are power on. Y2 will show that the comparator has verified the transmitted packet count successfully, and Y3 confirms that the computer are power on and the comparator is functioning correctly, and Y4 shows that password verification has been successfully completed. Y5 confirms that the computer are power on and the password verification is successful, while Y6 indicate that both password verification and comparator functionality are working correctly. Lastly, Y7 will light up when the packet transmission has been successfully completed or no data is selected and transmitted, it yielding a valid result in the comparator. The third feature is Advanced Fault Detector. This can enable a quick identification and resolution of faults via LED indicators and the decoder. We have implemented two decoders. The first decoder will monitor errors on power status of computers in both labs, clock signal for the counter, and also status of the multiplexer. While the second decoder will monitor the errors on status of the clock enable, status of the clock comparator, and status of the multiplexer. Based on the LED lights up, we can identify which component in the system where the error happens in by referring to the error code stated beside. While the last feature is the integration of monitor, dashboard, and fault detector. It can ensure system remains efficient and focus on active operations only. We have connected Y7 from monitor dashboard that indicates successful packet transmission completion and connected it to the enable pin of both fault detectors, which is decoder 1 and decoder 2. And the effect on the fault detection is once data transmission is completed, the fault detection of the system is disabled. This can prevent unnecessary fault detection or error reporting after the transmission is done.
So now I will demonstrate to you how our circuit works. First of all, you have to set the preset and clear of the counter of the circuit to become 1 to make it synchronous. So next, you have to choose which computer in lab 1 to transmit data and which computer in lab 2 to receive the data. So in my case, I will choose the first computer in lab 1 to transmit data. So now I turn on the power. And the second computer in lab 2 to receive the data. So I'll turn the power. So now we have to make sure the selected pin of the mask is correct. So here is 000, which means the first computer. So here I have to make it 001, which means the second computer. So now let us enable the clock, which can be seen as the data. So now we can see the AND gate is providing a positive signal. So now let us select the number of data packet that we have to transmit. So for here, I will choose add packet. To activate the clock enable, we have to make sure all the 5 inputs are providing positive signal. So we still have left 3 input to become positive. So now I turn on the ready TRX. And for here, one of the input, which is the password. So you can see the default password of the system is 110. So to make it provide the positive signal, we have to input the select password to activate the clock enable at the same time. So here is the monitoring dashboard, which shows the status of transmission of the data. So now the LED in output Wi-Fi is turned on, which means power is on, power of the computer is on, and the password is okay. So here is the fault detection monitoring dashboard, which is also one of the advanced features. So we can see the LED at 3 is turned on, which means the demarc is not working, and here says the clock enabler is not working. So now let us transmit the data packet. And also here is the screen to show the number of packet transmitted. So every time I push the pulser, one data packet will be transmitted. Once the number of data transmitted is same with the number of the data packet selected, the counter will automatically stop. So this will eventually deactivate the clock enable, since the comparator is providing a negative output signal. So here we can see the LED at the output Y7 is turned on, which means all packets are successfully transferred. And after all data packets are successfully transferred, the fault detection monitoring dashboard will be turned off. So that's all from me. Thank you.
Last but not least, we arrive at our conclusion. As a group of 4, we work on designing a solution for a data transmission system using the concept from chapter 6, 7, and 8. By using this, we collaborate through discussion and research to create a logic circuit with added features like error detection, and password protection. Some of the design features we put it inside our projects, which are counter-out counters, comparators, clock signals, and clock enable pin to control deep flip-flop counters operations, monitoring dashboard for packet transfer verification and fault detections, as well as additional features such as password protection for secure operations. Our logic components used in the project is marks and demarks for single-line data transmission and routing, decoders which are used in dashboard and fault detections, comparators to ensure packets and passwords accuracy, as well as a synchronized counter which are used in our deep flip-flop for triggering the flip-flops in parallel to halt at a packet limit. This project deepening our understanding of combination logics, counters, and system functionality while allowing us to design a reliable system with error detections and monitoring features. That's all from us. Thanks for watching.